important points that you have to take note of. Generated EMF is a result of all the EMFs generated in the coils which are in series between the terminals. And we said in a wave-wound machine, it is 2 number of parallel parts, and in a lap-wound, it is P. And then you can get an explanation for that. But then the generated EMF EA will be the terminal voltage or the general voltage in the generator, or the back EMF in the motor. So those are the two ways in which we still look at the same generated EMF. And then on the torque, we say the torque is a result of the forces on the current carrying conductors that are interacting with the magnetic field. And so the overall force will be the force due to individual conductors, which produce a moment of force or a torque in the same direction. And then the torque will be equal to Ka phi Ia, right? And then we said the power now generated in the motor and in the generator, they have the same expression, meaning to say ideally the same mechanical power used is the same magnitude as the electrical power developed. Though later we'll realize that this is not the case due to the issue of losses and other unideal conditions that exist in our electric machines. Right? Power in the generator, the mechanical power is 2T omega M Ka phi Ia omega M, and the electric power again Ka phi omega M Ia, and ideally again the mechanical power that you give into the field is the same electrical power that you generate out of the field. Remember, we are saying ideally, meaning to say that should be what we expect in a perfect setup. That is what we should expect in a perfect setup. That's the ideal condition that we are talking about. Perfect setup where there are no losses, all other things are the same. That's the ideal condition which we are talking about. Right. Then we go on to DC machine ratings. For the purpose of this study, we'll consider the rating with respect to the armature. So we talk about current and voltage in respect to the armature. Remember, it is in the armature where we talk about generated voltage and also the force experienced by the conductors. Otherwise, the field is just there to give us the flux. So let's take a simple example and see if we can apply the simple theory that we put in there to make calculations. So in our example, we are talking about a 4-pole DC machine, which is an armature winding of radius 12.5 centimeters, and it has a length of 25 centimeters. The pole covers 75% of the armature periphery, and the car armature winding consists of 33 coils, each having 7 turns. The coils are accommodated in 3 slots. The average flux density under each pole is 0.75 Teslas. So if the armature is lap wound, right? So things to note is the number of poles. P is equal to 4, right? Then the length, 25 centimeters, radius 12.5, poles covering 75%, that is 3/4 of that. Number of coils, 33, turns per coil, 7 turns, right? Then average flux density, which is our B, becomes 0.75. And the machine is lap wound. So from the above information, you will now check if the machine is lap wound. What do we get? P is equal to 4. Machine is lap wound. How many parallel paths do we have? And so on and so on. So before you continue to answer the question, you should also look at the information that you're given and how it can help you to simplify the problem. So if the armature is lap wound, first question was calculate the machine constant. That is, machine constant, you should know that machine constant is Ka. So that makes things easy for you. If you know that the constant is Ka, then you can calculate the machine constant. Then the generated voltage when the armature rotates at 100,000 RPM, that's revs per minute. Then the current in the coil and developed torque if the armature current is 400 amps and the power developed by the armature. So those are the things that we have to calculate. So the first thing we want to find N, we said N is the total number of turns. So N, in that case, we have 33 coils, each with 7 turns, so we have 231 turns, right? Then Ka, that's number of turns, number of poles, by A. Remember, A is the number of parallel parts. Lap wound, that means there should be 4, right? Then Ka becomes called 73.53. That's your machine constant Ka. Then the second question was the generated voltage when the armature rotates at 1000 RPM. So effective pole area is given by A, which is called the stator inner peripheral area times percentage covered over the number of poles. Why do we need the total area? Because we have flux density, so we have to be able to calculate flux. So we need the area. So in that case, we find the area using the dimensions given, right? Now, the 75%, if you go back, it's covering 75% of the armature periphery. That means the total area of the armature, 75% of it is also the area of the poles. That's why we use that 75%. Then after that, we can now calculate our flux per pole, which is 5. And this becomes area times flux density, you get that value. Then the angular speed now, omega m, that's 2 pi times number of cycles per second, which will be 2 pi n over 600, or n in RPM. That's why we divide by 60. So that will convert to RPS, revs per second, which will be a frequency, because you know that omega is called 2 pi f. So you have to be able to calculate the frequency of rotation. So it's 1000 over 60, right? And you get your angular speed is 104.6 rads per second. Then after that, you can now calculate the induced armature voltage, EA, being equal to Ka 5 omega m. Ka 5 omega m. And you get your 212.5 volts as the generated voltage. Then the current in the coil becomes equal to armature current divided by the total number of parallel parts. Remember, I said there will be number of parallel parts there, but then the armature current is the one which is entering into the armature. So the current in each coil will be equal to the total current divided by the number of parallel parts, assuming that the coils are uniform. They have the same parameters and you get 100 amps. Then torque developed by the armature now becomes equal to Ka5 Ia, and you get your 811.8 Newton meters as the torque developed. Then the power developed by the armature P is equal to Ka5 omega m Ia. That's torque times speed. and you get 85.0 kilowatts is the power developed by the armature. So that's basically how you make calculations using those parameters of the machine. Now, we have made some assumptions about a machine so that we can simply go and make those calculations. But you realize that the conditions tend to change. So you realize that we've put a linear relationship between flux and the speed and generated EMF and developed torque and so on. But the reality is there is a point when those relationships cease to be linear. Why? Because when you're magnetizing a magnetic material, like we said in our first lecture, then there comes a point when the material becomes saturated. That's why I want to talk about magnetization curve, right? So this is also called the saturation curve. Field MMF and armature MMF are at 90 degrees to each other, that is quadrature. That means you can actually ignore the armature MMF for a pole, and that means the pole flux would depend basically on the field current and the reluctance of the magnetic circuit. This is true at low fluxes where the core can be assumed to have zero reluctance. That means you don't need any energy to establish flux in the material. And that means the flux now will depend basically on the reluctance of the air gap, right? And in that case, the flux will increase linearly with field current. That means as you increase the field current, assuming the air gap reluctance is constant, then the flux will increase linearly. But as the field increases, then the saturation in the core, and hence the flux will cease to be increasing linearly with current. And that is the situation. So you have a linear portion, then there is also a portion which doesn't become linear. So the objective in machine design now will be to try and operate in the linear range so that the design parameters will come out as they are. So the design will try to make sure that the machine operates in the linear range. The machine operates in the linear range. Now, flux MMF curve will be similar to the EMMF MMF curve, because we've said the flux will be linear, and hence there will be a linear relationship between the flux and the EMF, and hence we have a linear curve. So you can see that this curve and that curve are the same. What changes will be the speed, so that the generated voltage will follow almost the same structure, but the speed will then determine the magnitude of the generated EMF, but the curves will still be looking similar, right? Then the classification of DC machines, this is basically due to the way they are connected. So we said the machine has a field winding and an armature winding. So the way the armature winding and the field winding are connected basically will determine what we call that machine. So if we say the machine is separately excited, we are saying the armature terminals and the field terminals, or the field winding and the armature windings, they are not connected from the same source. That means they are separately excited. So this is a separately excited machine arrangement where the field windings are supplied by one source, and the armature winding is connected to another source. Then there is a series wound where the armature and the field are in series, which means we only have one source of EMF connected to both the series and the armature winding, which means the armature winding and the field winding currents will be the same. Then there is what is called a shunt machine. That means it's shunt wound. The field winding and the armature winding are in parallel. They are supplied from the same source. But then you realize that in this case, they will have two different currents. So in series wound, armature current is equal to field current. In shunt wound, the armature voltage is equal to the field voltage because they are in parallel. Then there's what is called a compound machine, which we have two separate field windings. One connected in series with the winding, and the other one connected in parallel with the armature winding. So that's again another variation of the type of electric machines. So for today, that is what we are going to, what we will look at. Then the next time, we'll then look at DC generators and DC motors in particular. So we got into the details of those. So you check your notes, and I think that should be chapter 3 and 4. Let's read those chapters, then we'll cover them in our next lecture. Okay, you can unmute if you have any questions so that we can proceed and end our lecture. Any questions from what we've talked about so far?
Yeah, I just want to say thank you, sir.
Okay. Regis, any other? Fine, so let's go and read chapter 2 and 3, is it? Yeah, chapter 3 and 4, I think, so that we can move on to the specifics of generators and motors in terms of DC. Then we also then move on to the AC machines. Yeah, I'm a bit slow at first so that you get what we are doing. Then later on, we'll pick up speed and move. Thank you and enjoy your day.